Section 4.6, a summary of curve sketching. By the end of this section, you should be able to analyze and sketch the graph of function. Analyzing the graph of function. When graphing a function, either using a graphing calculator or some kind of, tools, computer, remember that normally it is not possible to show the entire graph. So we need to decide which part is, often crucial for our need. For example, let's say here, the first one and second one, both of them represent the same function. But the first one, the domain is later restricted here from -2 to +5. And second one, it's from -10 to +30. But by seeing both views, it is clear that the second viewing window gives a more complete representation of the graph. But would a third viewing window reveal other interesting portion of the graph? To answer this question, we are going to use calculus to interpret the first and second derivative. And that is the goal of this section. While plotting the graph, these are the steps or points we can keep in mind. So first of all, if it's possible, find the domain. It's always possible. Finding the range could be sometimes tricky. So always find the domain. If it's possible, find the range as well. If it's not possible, you can, just leave it for the range, but find the domain. Second, after finding the domain, find the intercepts, asymptotes like horizontal asymptotes, vertical asymptote. Later in the section, we're going to talk about how to find the slant asymptote as well. And then also symmetricity of the graph. That will also save our time while sketching the graph. And then we need to find out the first derivative and second derivative. And using the first derivative and second derivative, we need to find critical numbers. We need to find inflection points if it's, if there is an inflection point as well. And that will, give us like relative extrema, relative maximum value or minimum value whenever there are relative maximum or minimum value. So these are some guidelines we can use while sketching the graph. Look at one example, sketching the graph of rational function. Here is a rational function. First of all, find out the domain. Finding the range for this rational function is not possible as is. We need to use, more information, and we need to use the calculus like first derivative and second derivative for finding the range. So you can wait for that. And finding the x-intercept is easy. Just put the numerator equal to 0 and solve for x. That gives us x-intercept. Y-intercept means just put x equal to 0 here, and then that will give you the y-intercept. Vertical asymptote means where this denominator equal to 0, that would be the vertical asymptote. Horizontal asymptote, it's from previous section. Because the degree on the top and degree on the bottom are same, the horizontal asymptote is y equal to 2. So these are the information we can find. For the domain, just make the denominator 0, solve for x. When you solve for x, 2 and -2. So these are two values which cannot be used inside the domain. So what is the domain? Domain is all real number except 2 and -2. We don't know about the range. X-intercept means just solve x squared minus 9 equal to 0, and that gives you 3 and -3. So 3, 0 and -3, 0 are the two x-intercepts. Y-intercept, find f of 0. If you put x equal to 0 here, that will be the 2 times -9 over -4, which is 9 over 2. So the y-intercept is 0, 9 over 2. Vertical asymptotes comes from here. So x equal to 2 and -2 are the two vertical asymptotes. Horizontal asymptotes, using the previous section, y equal to 2 because of the same degree. So these are the information we have found. But we can find more information before we plot the graph. But this information also gives us a lot of information about the curve. So we know there is a vertical asymptote at x equal to 2, at x equal to -2. We know the graph is passing through these points 3, 0 and -3, 0. We know there is a horizontal asymptote at y equal to 2. So this is the horizontal asymptote. Okay, and now we know the y-intercept is at 0, 9 over 2. So this is y equal to 2. 9 over 2 is greater than 2. So somewhere here the graph is passing through this point. So we already know this information, but that's not enough. We need to use calculus to complete the graph. So for that, we need to find out more information. We can find symmetricity of this graph by finding f of negative x and comparing with the function itself. If the first thing is true, that means the graph is symmetric with respect to the y-axis. If this second statement is true, then the graph is symmetric with respect to the origin. And then we can find out the first derivative by using the quotient rule here. We can also find the second derivative by using the quotient rule. And by equating the first derivative with 0, we can find the critical numbers. And then for the inflection point, which is a point where the graph changes the concavity, we need to first find the second derivative and we need to find the concavity. So this one, we can talk about this after finding the testing point from the test interval and finding the concavity. Okay, so after finding this information, I'm not finding it. You can do this, just replace x by negative x and compare with the first one. That would be actually equal to the given function, because if you look at the function here, x is square. So if you replace x by negative x, eventually it's going to give you the same function. So that means the first assessment is true, which means the graph is symmetric with respect to y-axis. By using the quotient rule, we can find out the first derivative, and this is the first derivative. By using again the quotient rule, we can find the second derivative, and this is the second derivative. And for finding the critical number, you just have to equate this first derivative with 0. That means the numerator part, which is 20 times x, should be equal to 0, which means x equal to 0. So that's the critical number. For the point of inflection, there is no point of inflection, but you can wait for this information after testing this second derivative on this test interval. Okay, after finding this test interval, how did we find the test interval? By looking at the domain. If you remember, the domain is it's going from at -2 and +2, the function is undefined. So you can divide this real number line into first, second, -2 to, and there is at 0 there is a y-intercept. So we can just find our testing interval from -∞ to -2, -2 to 0, 0 to 2, and 2 to infinity. So these are the intervals we can use for testing purpose, where our function is increasing, where our function is decreasing, where our function is concave up, where our function is concave down. We can use this interval and we can test that. So to save our time here, I'm going to summarize this information here. This is the table, this is the interval. We would like to test the function. The first derivative on this interval would be negative. If you go back and check your first derivative, the first derivative is actually 20x over x square minus 4 to the power square here. So this denominator part is always positive because there is a square. So the value of the first derivative depends on the value of x. So if we are taking x from negative part, this interval, the first derivative would be negative. Even here, if you take the value from here, the first derivative would be negative. From here, the first derivative would be positive. And from here, the first derivative is positive because, as you can see here, our first derivative depends on the value of x. If x is positive, the first derivative is positive. If x is negative, the first derivative is negative. And if you look at the second derivative here, no matter what x value you pick, this is always positive. This is so this is a little bit tricky here. If you pick something less than -2 from here or greater than +2, this part would be positive, right? This is always positive because of a square, and there is a negative, so -20 times positive is negative. So on this interval and on this interval, the second derivative is positive. But what about here? If you pick something from here, let's say 0, then your second derivative would be actually positive. So that will help us for finding where the second derivative is positive and where the second derivative is negative. And we can do that by using some testing points. So on this interval, first interval, the first derivative is negative, second derivative is negative. Keep in mind, here the first derivative is negative, the second derivative is also negative. Okay, so we can always pick a testing point from here, like let's say -4, and plug the value, and that will give us where it's positive and where it's negative. So on this interval, because the first derivative is negative and then second derivative is also negative, the function is decreasing and then concave downward. Because second derivative is negative, it's a concave downward. So something like this, it's going down and then concave downward. You understand? So where it's happening? From -infinity to -2, the graph should be look like this, concave downward and decreasing. That's the meaning of that statement. Okay, now at x equal to -2, the function is undefined, the first derivative is undefined, the second derivative is undefined because there is a vertical asymptote. On this interval, the first derivative is negative, that means function is decreasing. Second derivative is positive. If you check the second derivative here, it's positive, so that means it's a concave upward. So the graph is from -2 to 0, -2 to 0, the graph is going down and then the concave upward like this. You understand? So that's the meaning of this decreasing and then concave upward. And at x equal to 0, we have that y-intercept, which is 9/2. First derivative is 0. If you try to find out the first derivative at x equal to 0, look at here, at x equal to 0, that's a critical number. The first derivative is 0. Second derivative is positive. By using the second derivative test, because the second derivative is positive and then first derivative is 0, that point you are going to have relative minimum. So here at 0, where the value of the function is 9/2, that's the relative minimum. So that means after this point, the graph has to go to up to be this point as a relative minimum. So that's the nature of the curve we're going to get from -2 to +2. Okay, and if you go further from 0 to 2, first derivative is positive, second derivative is positive, meaning is the graph is increasing because the first derivative is positive, and second derivative positive means the graph is concave upward. So that's why the graph is increasing, going up and then concave upward. Okay, similarly at 2, function is undefined, so there is a vertical asymptote from 2 to infinity. The first derivative is positive and second derivative is negative. That means the function is increasing and concave downward, increasing, concave downward. So how that's possible? If you remember, the graph on the left side we drew, it was like this. From up to -2, it was like this. Now after +2 to the right side, graph is increasing but concave downward. So something like this, it's increasing, going up, but concave downward. So by using all this information, we can complete our graph here. So here the graph should passes through the 3, 0. It should be increasing and then concave downward, and this y equal to 2 should be the vertical asymptote and horizontal asymptote, and x equal to 2 should be the vertical asymptote. So you should draw the graph like this. Here from -2 to +2, this is the relative minimum, so graph has to be like this. And then here the graph should passes through -3, 0. So the graph has to be like this. So remember, the nature of the graph I drew, like concave downward, decreasing, concave upward, decreasing first and then after that increasing, concave downward, increasing. All this information I got from first derivative, second derivative test and this testing interval. Eventually, this is the actual graph we're going to get, and that can be found using the calculus. Okay, so always you have to use a first derivative and second derivative for finding the nature of the graph. Let's look at another example. This is also rational function. We can find the domain. Domain is all real number except 2, because at 2 the function is undefined. Range, don't worry about the range because it's a tricky part. Like in previous problem, after plotting the graph you can find out the range. Look at here. What is the range? Range means from negative infinity. It's range means it's a y value, so it's there is no boundary when you go down. So you start from negative infinity, go up to 2. At 2, that's the horizontal asymptote, so you don't include 2. Union, and then this is the relative minimum. 9/2 is the relative minimum, so you start at 9/2 and you go, there is no boundary on the when you go up, so that's why there is an infinity. So this is the range, and that can be found by using the calculus. Initially we did not have any idea how to find the range. Similarly in this problem, don't worry about this. Eventually after using the calculus we will be able to find out this range. Okay, and what about the x-intercept? Meaning the top part's supposed to be 0, but for what value of x the top part is 0? The answer is none, because you cannot solve this quadratic equation on the top. What is the y-intercept? Put x equal to 0 here. That will give you 4 divided by -2, which is -2. What is the vertical asymptote? X equal to 2. Horizontal asymptote, because the degree on the top is greater than the degree on the bottom, so there is no horizontal asymptote. Situation like this, we can find slant asymptote, and I'm going to talk about that right after this problem, how to find the slant asymptote, but horizontal asymptote is not possible. Now what about the symmetricity? None. By using the very same idea we use in previous problem, we find the f of -x and compare with the f of x, and that tells us there is no symmetricity. And then the in behavior, we can find the in behavior of this graph when x approaches to infinity, because there is no horizontal asymptote. What about the when x approaches to infinity in behavior? The function would approach to infinity as well. So you know how to find it by we covered this thing in previous section. First derivative, use the quotient rule. Second derivative, again use the quotient rule. Now compare this first derivative with 0, so that means solve the numerator equal to 0, and that will give you x equal to 0 and x equal to 4. These are the two values, which is a critical number. Point of inflection, don't worry about that. You need to check where the function is concave upward, where the function is concave downward, and where the function changes the concavity. So eventually the answer is none, but that can be found by testing this testing the value of the second derivative on this interval. How do you find this interval? Negative infinity to 0, 0 to 2, 2 to 4, 4 to infinity. That can be found by using the domain, which is 2, and then y-intercept, which is 0 and -2. So you can see here negative infinity to 0, 0 to 2, 2 to 4, 4 to infinity. Why I'm using 4 here? Because of we have a critical number at 4, and we would like to find out either there is a relative maximum or a minimum value at those critical numbers. So first of all, draw a real number line, and then find the domain. From the domain you can see that all the real number except 2. So at 2 there is a vertical asymptote. So after that, put this critical number is at 0, at 4. So now you have 1, 2, 3, 4 different interval from here: negative infinity to 0, 0 to 2, 2 to 4, and 4 to infinity. Now we're going to check our first derivative and second derivative on those 4 interval. For a checking part, you can pick your testing points as you wish, and after that you can find out where the first derivative is positive, where the second derivative is positive or negative, and based on that information we can say where the function is increasing, where the function is decreasing, concave upward, concave downward type of thing. I'm going to collect all this information in this table here. On this interval, the first derivative is positive, that means function is increasing. Second derivative is negative, that means the concave downward. So look at here, from negative infinity to 0 the function is increasing, but it's concave downward. So how do you do that? So and what about this function is positive or negative? we don't care about that for now. So it's increasing and concave downward. So something like this. Okay, something like this, increasing, concave downward. And I'm not saying this is the negative value. Okay, I'm just giving you the nature. It's increasing but concave downward. At x equal to 0, the value of the function is -2, and then first derivative is 0 and second derivative is negative. Using the second derivative test, at x equal to 0, you are going to get the relative maximum value. So relative maximum value at x equal to 0. So what is the value of the function at -2? So that is -2. So the graph on the left side, if you look at here, here -2 is here, the graph would be look like this. You see, at x equal to 2, there is a vertical asymptote at x equal to 2. So somehow it should come down here because it's a vertical asymptote. So this graph should approach this x equal to 2 like this. Okay, and that's because of concavity, concave downward, increasing up to 0, and then after that there is a relative maximum at 0, and then it goes down because it's a relative maximum. There is nothing more than that, and then it should go down because it's a vertical asymptote. At x equal to 2, it's a vertical asymptote undefined. From 2 to 4, we are here, 2 to 4. The first derivative is negative, that means graph is decreasing, and second derivative is positive, that means the curve is concave upward from 2 to 4. Okay, at x equal to 4, if you check the value is 6, so that means it's a positive value. At x equal to 4, the value is 6, somewhere here, positive value. Now we know it's increasing here. If you focus, the graph is decreasing and concave upward. So how do you do that? Graph is decreasing, concave upward, and at x equal to 4, the value is 6, and the first derivative is positive. First derivative is 0, second derivative is positive, that means relative minimum. At this point, the graph has to be a relative minimum. It's decreasing and then relative minimum and then concave upward. So how do you do that? Decreasing from 2 to 4, it's decreasing, concave upward, decreasing, concave upward, like this. It's going down, decreasing, concave upward, and at this point it's a relative minimum, and from this point it will go up because here is the relative minimum. And on this side, because it's a vertical asymptote, the graph should approach this this vertical asymptote. So the graph of this function would look like this. Okay, so that's the graph, relative maximum, relative minimum. Now after looking at this relative maximum, relative minimum, we can find out the range. Look at here, from -infinity go up to -2, and then start from 6 up to +infinity. So that's the range is from -infinity up to -2, union from 6 to infinity. You see, in between -2 and +6 there is no value, so that's the range. Okay, and what about the concavity? Concavity, it's concave downward and again downward, so there is no change. It's concave upward and again upward, so there is no part of the graph where concavity is changing. That's the reason there is no inflection point. That's why possible point of inflection is now. That's the graph. One more thing I told you I'm going to talk, and that's for this function. If you look at here, for this function, if you look at here, if we try to find the horizontal asymptote, the degree on the top and degree on the bottom, they are not same, and so the degree on the top is 1 degree greater than the degree on the bottom. Whenever you have this case, the 1 degree greater than degree on the bottom, always divide the top part by the bottom part and then write down the leftover thing here. So this is the quotient and this is the remainder. That will help us for finding the slant asymptote. How do you find the slant asymptote? The slant asymptote would be y equal to x. When x approaches to infinity, this value goes to 0, so the function goes to y equal to x line. This line is called slant asymptote. The graph of a rational function having no common factor and whose denominator is of degree 1 or greater has a slant asymptote when the degree of the numerator exceeds the degree of the denominator by exactly 1. If it's exactly 1, only in that case we can find the slant asymptote. To find the slant asymptote, use long division to rewrite the rational function like we did here as the sum of the first degree polynomial here and another rational function. This is the rational function. So we can divide, and this one, y equal to this value, whatever value we get here, that would be the slant asymptote. What does that mean? That means this y equal to x line, if you look at the y equal to x line, the function, the graph of this function approaches to that line when x approaches to infinity or negative infinity. That's the meaning of slant asymptote. So after plotting this slant asymptote, we can sketch the graph more accurately. Okay, so sometime horizontal asymptote is not possible, but slant asymptote could be possible like this.